Good morning, everyone. How are you doing today? If you don't remember me, because I was on Zoom last week, I'm Dr. Pat Layton, and I am the director of the Wood Utilization Design Institute and a emeritus faculty in forestry. And just remember that before you leave, please sign in because we do have to take roll. The university gets very upset if we're not taking roll for this. So with that, we have about 1 more minute. Any questions about what's going on? Everybody got their quiz materials, and I know in engineering and F&R we're doing that. And then the readings, we'll be posting readings for next week. And there'll be a small quiz prior to that. And my computer is telling me it's time to start class. Hang on a minute. So with that, I'd like to get started. As you know, we covered the carbon record from Weyerhaeuser last time on top of our introductory seminar, and I hope you saw the flow of that. Several times during that survey, I'm sorry, I have to be on or nobody can hear me. We found after that LCA becomes a very important topic. So the life cycle analysis, and that is not very old. Life cycle analysis actually started in the late 1980s, and it was really tasked by a lot of environmental toxicologists. They kind of set up the first analysis of life cycle analysis. Doing inventories. They were looking for really bad stuff in the waters, air, where was it coming from? And a lot of the Society for Environmental Toxicology did the original development on that. It has gone on to be a very famous and fortunate tool for us. And it can give you information leading to environmental product declarations or statements about products. The tricky part of LCA to me, though, is defining the product or service and the boundaries around it. That's always the tricky part. And if you don't know a lot of stuff about it, the boundaries from one product to another could be different. And if you're trying to compare, you may not have a good comparison. But we're going to learn more about today about LCA. We're joined by Dr. Indroneil Ganguly. He is an associate professor in the School of Environmental and Forest Sciences and the associate director for the Center for International Trade in Forest Products at the University of Washington. We had hoped that he would be here in person, but things have kept us on other sides of the coast. So he's joining us early this morning from out in Seattle. And he is going to be talking to us. I will say that he's been involved in LCA for a long time, and I've actually been on several panels with him in the past because, believe it or not, years ago, this is how your life will change, you won't know. I actually worked on an International Organization for Standardizations, that's ISO, panel that actually wrote the first standards for life cycle analysis. That was in the early to mid 90s when I was doing that. So years ago, long time ago. So another lifetime, it seems like. And it's still here. It's sort of like biomass energy. I did that once a long time ago, and it's still here. So Indra, take it away. You're on mute.
That was a great introduction to life cycle assessment. I really liked it, and you primed the group up for the discussion. So as Pat mentioned, and thank you for inviting me here, Pat, and thank you, students, for being here. I like the crimson red colors. I wonder why that is crimson red of the chairs there. So I'm with University of Washington. I'm a fan of purple, not so much crimson red. So I will show a lot of purple on my slides. And as Pat mentioned, I've been working on life cycle assessment for a while. And I was hoping to be there in person, meet you guys, but I thought that it would be like another trip. I can make it and come back, but tomorrow I have a meeting and all the connections and everything I need to take from between the two cities. It's quite a bit of an ordeal, and I couldn't manage a connection that would get me back in time. So apologies for not being there in person. I really would have enjoyed to talk to you and meet you guys in person, but here I am. You're seeing my face bigger than you'd have seen in real person, so you'll be able to recognize me better when you see me. Other than my height, you have no clue what my height is. So anyway, let's get started. I'll share my screen. Hopefully that will work. Yes, I do have shared screen option. Okay. So I hope you can see my all purple screen there with the title. Yes. Okay. So I'll talk a little bit about biogenic carbon neutrality. I'll talk about embodied carbon a little bit, give you a brief overview of LCA, and then introduce a comparative whole building life cycle assessment. A comparative will take a look at two buildings and compare the carbon footprint of the two buildings. And the whole idea is trying to do an apples to apples comparison. And if you're looking for readings, I have put a few papers in here for you or your students to take a look at. And maybe there's more readings you'd like to have, but at least you have some in here. So I will start with some definitions. And before I move forward, I cannot see the room very well. So if you have a question, please voice out, interrupt and voice out, it's fine. Or you can also put it in chat. I'm not sure if I'll be able to monitor the chat though. So I encourage you to voice out if you have any questions. I'll be happy to answer.
Our speakers may not be on in the audience, but I'll try to watch. But if you put your questions and they don't actually have the content, wave at me. They're not on Zoom with you. So, and we'll monitor the chat for the outside audience. But if you have questions, I'll sit so I can see. Okay.
Perfect. Thank you, Pat. So I'll start with some definitions, and we hear these terms all the time. Often we get confused ourselves on what these terms use. The first term I want to introduce is called carbon pool. Carbon pool is think of a reservoir of water, and when we think about a reservoir of carbon, it's called a carbon pool. What could be a carbon pool? A forest could be a carbon pool. It's a reservoir. And it's almost like a stock, a reservoir of water. So then I am saying carbon stock. Stock is the absolute quantity of carbon in that carbon pool. So stock, when we talk about stock, we are doing a little bit more numeric. The term is carbon pool is a general term. Carbon stock is a little bit more technical term when we are saying, okay, there's X cubic meter or X tons of carbon in that carbon pool, and that's the stock of carbon, and that's called carbon stock. Now, there are two terms I will simultaneously introduce. One is the sequestration and flux. Now, sequestration, let's talk about flux first. Flux is carbon flux, which is the last term here. Carbon flux is when a pool either depletes in carbon, that is, the carbon in the pool goes down, or the carbon in the pool goes up. So the changes in the stock of carbon in the carbon pool is known as carbon flux. Okay. So the flux can be a positive flux and negative flux. Positive flux is when carbon leaves the system. Negative flux is when carbon enters the system. So carbon sequestration is uptick. It only happens in a few kind of carbon pools. One of them is forest. Forest has the capacity of sequestering atmospheric carbon into the forest or into the trees, and the trees grow. So forest was a carbon pool. We can account the amount of carbon in that forest using a carbon stock assessment. And the sequestration is a method of putting carbon, adding carbon to the pool. And so it is only the negative flux, that is carbon being added to the system, which and the carbon pool increases. And sink is when you are growing a carbon pool, it's called a carbon sink. When a carbon pool keeps growing, it's called a carbon sink. So a good forest is a carbon sink. A bad forest is a carbon source. The opposite of carbon sink is carbon source. When a forest leaves carbon more than it grows, it's a carbon source. A forest that sequesters more carbon than it leaves is carbon sink. All right, enough with the terms now. Let's move on. So, I have more terms. Fossil carbon, biogenic carbon. So I won't tell you to raise your hands, but because I won't be able to see, but hopefully some of you know fossil carbon and biogenic carbon and what's the difference. The difference is, to be very clear up front, chemically, there's no difference. Carbon is carbon independent of the fact it's coming from a fossil source or a biogenic source. A fossil source would be anything that has been fossilized over millions of years. Petroleum products are pools of fossil carbon. And biogenic carbon is any carbon that is in a biological form, and a forest is a pool of biogenic carbon. Chemically, they're identical. However, there are fundamental differences when we think about global warming and fossil carbon versus biogenic carbon. The whole idea of fossil carbon, we extract the fossil carbon from underneath of the earth and emit it either through combustion in industrial systems or in cars, or all the systems we can think about, or in your barbecue grill maybe. Or maybe you're not barbecuing with coal. So, all right. But any of the industrial systems, wherever you're burning fossil fuel, you're emitting this non-biogenic CO2. The difference between a fossil-based system and a biogenic-based system is that a biogenic carbon pool is what we call renewable. There is a system that brings the carbon back in, and when you harvest and let's say burn it, it emits back in the atmosphere. So one of the difference, you can say that fossil carbon is millions of years old carbon that was not in the circulation in the atmosphere and is added to the atmosphere. But biogenic carbon is in circulation in the atmosphere, sequesters and puts it back. And I'll go over that in a little bit more. So when you look at carbon cycles, so whenever we emit this fossil carbon, this is called anthropogenic emission because humans are causing this emission. This carbon was locked under the ground for millions of years, and fossil fuel can be coal, natural gas, crude oil, and the flow is one way. There is no way of sequestering that back into that into the previous form. So when we emit it, it's out of our hand. We cannot do anything. For a biogenic carbon, on the other hand, follows a natural carbon cycle. When we emit it, we have a way of sequestering it if we are doing forestry and harvest practice responsibly. And that's very important, and we'll emphasize on a little bit on that. And it's a two-way flow. It's important. We have a way of sequestering and emitting. So the flux is actually two ways in biogenic carbon. The flux is one way in case of fossil carbon. Let's go a little bit what global warming is and how why is it important to distinguish between fossil-based carbon and biogenic carbon and the role of forestry. So this is my amazing graphic of the Earth's surface. Okay, the green is Earth's surface. The layer on top of Earth's surface is atmosphere. It has a lot of greenhouse gases, and then there's space, and there's sun in the corner. Now, the greenhouse gases in the atmosphere play a very important role. It's essential for humanity and all organisms to thrive. So greenhouse gases are all not that bad. So it's like drinking alcohol, I guess. You guys are students. Maybe some of you are not drinking age. Maybe none of you are drinking age. But what doctors say in moderation is good. So greenhouse gas is like that. In moderation is good. Why? Because when the solar radiation from the sun reaches atmosphere, it just penetrates through. It has a very small wavelength, very high frequency. It penetrates through the atmosphere. It doesn't warm the atmosphere, but it hits the Earth's surface and heats up the Earth's surface. And then some of the heat radiation tries to leave the Earth's surface. Now, greenhouse gases actually stop this heat radiation because heat radiation has a larger wavelength, and they get stopped by a system. I'm not going to talk about it. And different gases have different ways of capturing this heat. They actually oscillate very fast, and it's called radiative efficiency of the gas. So all these greenhouse gases actually stop that heat from leaving the Earth, some of the heat, and some though leaves the Earth. So that heat is very important because that maintains a temperature around the atmosphere, and so that it makes it comfortable to live in. Now, what happens in case of excessive, when you're emitting fossil carbon? This is a pictorial representation. We are emitting new carbon of greenhouse gases to the atmosphere. So these were not in the atmosphere at this point. We are adding it. Now, when we are adding that, the potency of the radiative efficiency goes up of our atmospheric gases. So more and more gases are stopping the heat from leaving the Earth. And so it is creating this greenhouse effect, the same we see in actual greenhouses, like nurseries and all that. And that's why it's called a greenhouse gas. Now, let's see the role forests can play in this. Okay, we'll talk about that. So to just summarize what I was talking about, there's this natural greenhouse effect, which is good. Greenhouse effect is not all bad, but human enhanced greenhouse effect, which we are seeing on the right-hand side of the panel, which too much greenhouse gas in the atmosphere, that is what is creating what it's not only global warming. We talk about global warming, but it's climate change. And we have been talking and experiencing a lot more of that climate change. And there are various aspects of climate change, but this is what's happening. Now, the role forestry could play here. So if we have some forest, what the forest can do, if you're growing forest, the forest is sequestering some of these greenhouse gases back into a locked form. It's not in the air, in the atmosphere anymore. And what that helps in release a little bit more radiation back into the atmosphere and bring us back to a healthy level of greenhouse gases in the atmosphere. So forests can actually help, and forests are one of the few natural systems that can help, and I think is the only natural system that can be implemented at a large scale. So here I'm saying growing forest. Where does the wood product come in? So now let's say if we are not, we harvest trees, and the automatic thing we would say, well, you're cutting down trees. How can it be good for the environment? Because you're cutting down trees, the atmosphere is going back to the atmosphere. Some of it you're sequestering in that beautiful set of houses you see there, but some of it is releasing back in the atmosphere. But it's a dynamic system. So as we are harvesting in sustainable forestry, what we want to ensure that the trees there, the number of trees or the carbon pool in the terrestrial ecosystem in the forest does not go down while we are transferring this carbon from the forest to buildings, which are wood products or furnitures or any of the products. So we are storing carbon now in two places, biogenic carbon or this atmospheric carbon. We are storing in the forest and we are storing in the building. And this is the whole idea of wood products can play an important role, but it can only play an important role if you are sustainably harvesting forests. That means we are making sure that the trees, actually the carbon pool in the forest are not going down while the biogenic carbon pool in our economy grows, and which is plausible, which we are doing at this point, but from our accounting perspective, it does not seem very intuitive, and that's why we see so much resistance on wood products and harvested wood products. But I can give you some, I will give you some numbers to show how it works. I do see a chat. I'm just pausing to take a look at the chat. All right, it's not for me, so I'll ignore that. Okay. Now, so when we are looking at within life cycle assessment, when we are looking at environmental impact of a wood-based system, so we look at three things. Number one, the amount of carbon that is sequestered in the product or locked in that product. So a beefier, let's say there is this card holder, wooden card holder box I'm holding in my hand. It has locked some amount of carbon. It was in the forest at one time, and now it's sitting on my desk. And so the amount of carbon I am locking out in this box is a good thing, because that carbon was in the atmosphere for a while, and now it's not in the atmosphere, it's sitting on my desk. So that's a good thing. The bigger the amount of carbon that is locked away, the better. Now, the bad thing is that to be able to get this box to my desk, we have transported, we have harvested the tree, we use fossil fuel for that. We transported, we use fossil fuel for that. We varnished and did all this work. We need a lot of fossil fuel to actually get this box to my desk. And that is the product emission. And what we call it is embodied carbon associated with that box and all the product emissions that is with it. So that is bad. So there's a good and there's a bad. And then the longevity of the product, how long the product stays locked away. Now, if a long-lasting product is better because the product emission already happened, and if you have a lot of wood locked for a long time, it's even better. And that's why there's a synergic role between the number one and the number three things I talked about, and that's what the arrow is about. So there are two good things, amount of carbon that is locked away and how long the carbon is locked away. And the bad thing is the product emission or fossil emission that happens. So these three things together, if they net out to be a net beneficial system, it's good. Now, let's look at the aspects of sustainable harvesting. So when we harvest trees, what we call in the Pacific Northwest, and also that is a similar way of harvesting in the Southeastern, and these are the two wood baskets of the world, of the country, Pacific Northwest and Southeast. We do practice what we call even age management, that is in this commercial forest. And even age management is we try to maintain the forest so that every year we can harvest a little bit and leave the rest on the forest floor to grow back. And that biogenic carbon from the forest after harvest get transferred into a wood products. Now, all of the wood products are not long lasting, and some are waste. For example, this pile you're seeing on the bottom of the screen there, that's the wood waste, the tops and branches, which have little use at this point, which could be used actually. It's waste because of economic reasons. In real life, it is actually in some countries around the world, people would value this a lot, but we don't. We burn it, we dispose it, we let it die and decay. The panel products and the lumber products, on the other hand, they end up into longer lasting wood product, sometimes houses which are extremely long lasting. So remember the three legs of that stool. So that's a very good thing, house. Now furniture and chairs and all that, they have a little bit shorter lifespan, but still they're good because they sequester carbon for an extended period of time. Paper, on the other hand, is not that long lasting, and it emits a lot of carbon, and it may be not as beneficial as the others. Now, people at times would say, oh, then the paper industry is bad, but the rest of the wood industry is good. And I would warn you against those kind of argument, because it's a system. For example, I think you guys are, a lot of you will have some interest in architects and all that. So when you're building a house, you're building all kinds of different aspects, not only living rooms and bedrooms. When trees grow, they grow in canonical form. Some trees grow smaller, they're not used in lumber products. And we need to take some of the smaller trees and the tops and branches and do something with it to be able to take good lumber. So if you look at a system, paper product actually comes from a system that also helps produce long-lasting wood products. So we have to look at paper not just as paper product, but coming from a system of wood products and forestry. And we'll have to see that if the net is beneficial or not, just though they don't have a huge stock. So all this fossil carbon that gets emitted in the process, we are trucking and we are using chainsaws, and we are trucking this wood that burns fossil fuel, diesel and gasoline and kerosene and all those things. Now, when we are transporting that to wood products industry, they burn fossil fuel in terms of electricity, natural gas, and all those things. So that also gets accounted for and emitted. And we have to combine all these fossil fuel emissions, and we call that as what we call the embodied carbon of the wood product. So the embodied carbon is a full accounting of all the fossil fuel emissions, or all the all the fossil fuel emissions that has taken place throughout the process from the forest to your building or furniture, all the transportation, that is embodied carbon. Now, in the process, we are also losing a lot of biogenic carbon, which is in the other color of CO2. Now, that biogenic carbon, will have to make sure that is it a carbon neutral system or not, and that would be my next slide. I will pause a little bit here and see if there are any burning questions or clarifying questions I need to answer. Just I'll give a 10 seconds pause and move on.
Are there any questions? Everybody getting this? Okay, we're good, I think.
All right.
No hands went up.
Okay, so let's, how many of you, I am seeing some of the students, how many of you know the concept or have heard of the carbon neutrality of biogenic carbon concept?
If y'all raise your hands, I'll try to give them a proportion. Have you heard of biogenic carbon or carbon neutrality? I see about 8 hands maybe going up out of the whole room.
Okay, thank you, Pat. So some of you have heard about biogenic carbon neutrality. What it means, I'll just go, and how it is extremely important to have a good understanding of biogenic carbon neutrality, when you are doing a wood products related LCA, because that's one of the areas the wood products LCAs are criticized in a way that ISO, the same organization Pat worked in and helped write the codes. I did not know that, Pat, but that's actually has a provision saying you can call the biogenic carbon as carbon neutral. What it means, remember my slides where I was showing that increase in atmospheric greenhouse gases? What it says that when you emit this biogenic carbon as CO2 or back in the atmosphere, it does not increase the greenhouse gas and the rate and the global warming potential of the atmosphere, because we have a system that's sequestering it, and that system is essential. And this here, a growing forest, means all the sequestration is happening. That is factored in when we think about biogenic carbon neutrality. So you see 5 arrows going down, and these are apparently trivial, but not so. Think about this 5 arrows going down. That is, this is the sequestration is happening. That is, atmospheric carbon is being transferred into wood and foliage and all those other things in the forest. Now, let's say if you harvest the forest in a year, and let's say those 5 units got sequestered in this year, and this year we harvested 4 units and burned all of it. Okay, we just harvested and just burned it for fun. So now if we look at this net system, what happens is we sequestered in this year 5 units, and we harvested 4 units and burned all of it. Now, what happened? Why is it carbon neutral? Because this year I took away 5 units, emitted 4 units. So those 4 units did not actually increase the atmospheric CO2, and so it's considered carbon neutral. So, and then it gives you the system boundary, which again Pat alluded to in the beginning of the class. The system boundary is looking at this forestry system and what is getting transferred between the air to the forest and back into the air. It's a net negative or at least net neutral. That is, this system, by emitting it, only the biogenic carbon here I'm talking about, not the fossil carbon. This biogenic carbon, if the net system is balanced out, all the emissions of the CO2 from burning this biomass pile does not increase the atmospheric carbon, and hence it's carbon neutral. And that only happens when we practice sustainable forestry, when we can show that our forest biomass or carbon in our forest hasn't gone down because of the harvest practices, which is essential. So without which actually, and this is true, and these are the numbers collected by FIA for Washington State. Washington State in a certain year in 2015 sequestered 21 million tons of CO2 in its private working forest, which are not the federal forest, the private forests like farm forests, which are harvested every year. And of that 21 new growth, annual growth, the annual harvest was 14.5. And if you factor in all the other emissions of decay and all that goes on in the forest, it's still a carbon beneficial that we are not this system. If you burned all of it, now Washington State did not burn all of the carbon that it extracted from the forest as wood, but had we burned all of it, it would still be carbon neutral. But what actually we did, we actually had this process of all the wood that got harvested. A significant proportion of it got converted to lumber product, and Washington State is the second largest lumber producer, structural lumber producer in the country, after Oregon is the number 1. And it also produced a lot of panel products and pulp and all that. And in this process, it also emitted a lot of fossil fuel and a lot of biogenic carbon. So And this is a net accounting that I created for Washington State, and I published a paper a few years back showing that the net Washington State's private forest products industry, even when we factor in all the fossil carbon emissions, and when we factor in the storage of carbon in wood, it's actually net carbon mitigated, that it reduces global warming. And so this stored carbon, now all the emitted carbon is neutral, but when we store this neutral carbon, it actually is called carbon beneficial or carbon storage benefit. So, and we will talk a little bit about the carbon storage. So we learned a few terms here. One is, we learned a lot of new terms, I think, but I think the carbon neutrality for even those 8 and the rest, it makes a little bit more sense of biogenic carbon and the conditions. We are also now introducing storage, carbon storage benefit, and we also learned another term of embodied carbon. Embodied carbon is all the fossil emissions that goes into a product for it to be in your hand. And that is true for the pen you're holding in your hand or the paper. Every product you're holding in your hand or the chairs you're sitting on all have an embodied carbon. Some of this product has a carbon storage benefit and some not. The wood products that you're holding in your hand, maybe a pencil, has a carbon storage benefit, but the chair you're sitting on does not. And that is important to note. Okay, now let's get to the comparative whole building LCA. And I will talk for another 10 minutes, and then I'll open up the room for discussions. So that will give, I think, another 10 minutes for discussion, if I'm not wrong. So
Sounds good.
I'll talk, oh, sorry.
That sounds good.
Okay, thank you. So I'll talk about this. This case study I'll talk about is published in this paper. I work with our Department of Architecture here, and Francesca was my postdoc at that point. And we worked on this, and this was almost the first comparative or apples to apples comparative assessment that came out from the US of whole building life cycle assessment, but we have published a few more. So this was at that point cross-laminated timber, and I'm making that assumption that some of you have heard about that term, and mass timber was new to whole buildings, and we did not have a code approved and all that. So with those in mind, we wrote this paper, but later on we published a few more. We'll talk about that later. So in this particular paper, the objective is we'll compare a traditional concrete building, reinforced concrete, the way we generally build buildings, tall buildings in Seattle. And we will create, we created a hypothetical model of a CLT mass timber hybrid building. And we used mass timber. Mass timber is, by the way, glue-lam is glue laminated beams and cross-laminated beams. And if you don't know, later on I can talk a little bit about that, but those are engineered wood products, and those products could be used to displace concrete and steel for structural applications of the building. So we wanted to conservatively use a hybrid CLT building at that point when we did not have the codes approved. We just took international codes and compare it to a real traditional building that was built recently. So a quick definition of cross-laminated timber, think of it as plywood on steroids, okay? So same different layers of lumber products are glued and laid at a 90-degree angle. To each layer goes a 90-degree angle grain, cross-grained to each other. They can be 3, 5, 7, or 11 panels thick. So this could be very thick. A three-ply panel would be around 4.2 inches thick. A 7-ply panel would be 9 inches thick. So these could be really thick panels, and this can actually go into actual structural construction and displace concrete and steel. So we actually, because of the disclosure issues, we could not say which building we picked, but we actually picked a building in South Lake Union that was recently built. We talked to the architects of the building. It was an 8-story mid-rise building. We took all the material input that went to that building, and the architect students actually modeled an apples to apples similar functional area CLT hybrid building so that we can compare the two. So we use CLT and concrete to displace as much as concrete and steel we thought we could conservatively and get approved within the Seattle's building code. But later on, we realized we were way too conservative. But anyway, we'll talk about that in a little bit. And we decided to use the exact same geometry. Now, we also actually, we did not do one. We actually modeled 2 different CLT buildings. And one of the things architects and builders and residents always talk about is the fireproofing. People think that, well, wood burns and is it safe? And so one of the carbon impacts we get in CLT buildings or any wood building is the gypsum board. And the taller you build the building, the more gypsum board you have to use as a carbon proofing. And so on the scenario A, on the left-hand side, you see there's some panels of CLT and gypsum board covering the panel for fireproofing. On the right-hand side, there's a concept called charring design. A charring design is we use some sacrificial layers of CLT or wood around additional wood we use in the CLT. For example, let's say the engineers say the structurally we need to use a 9-inch panel, and we would use an 11-inch panel. And so the whole idea is wood, when wood burns, it has a characteristic called charring. When wood chars, charred wood is an excellent heat insulator of heat. So it stops heat from transferring. So once the wood chars, it protects the inside layer. So a charring design actually would give us the same impact of gypsum wallboard. The only problem is that we use more wood and it becomes a little bit more expensive because wood is expensive. System boundary, also something we talked about beginning of the class. There are actually in product stage and construction stage, there are 5 levels, A1 to A5. In this particular paper, we modeled A1, which is the raw material, transportation, manufacturing, and manufacturing all the raw materials. We also did part of actually construction at site and installation, but we expanded those in our later work. So this is the system boundary. We did not have the operational life of the building or demolition of the building or maintenance of the building. Those are outside the scope. Now we start with what we call a bill of materials. So here there are 3 rows. So these are all the components. There's steel beams, concrete slabs, columns, which are either glue lamp columns or steel rebar columns, steel with concrete columns. We created a whole list, and this is just a summarized list here. And these 3 columns over here you see are the 3 different configurations. The first one is reinforced concrete building. The second one is the hybrid CLT building with gypsum fireproofing. And the third one is the CLT hybrid building without gypsum fireproofing, but with that additional wood sacrificial layer, and we call it charring design. So these are the 3 different scenarios. And within life cycle assessment, there are a number of impact categories. I didn't talk about that, but so there are impact categories that are approved by this this acronym called TRACY. This is a method. This is an EPA approved method. And we are using global warming, ozone layer depletion, smog formation, acidification, eutrophication. Global warming is the one we generally always emphasize on. It is the greenhouse gas aspect, how much net greenhouse gases we are adding to the atmosphere, and as a result of it, over the next 100 years, how much increase of radiative forcing in the atmosphere we encounter, and that's the global warming. There are a combination of local and global impacts here. Smog formation is a local impact. Ozone depletion and global warming are more of a global impact. The energy consumption is one of the areas we also invested, because that's something a lot of people are interested in. What is the total energy and used in building that building, and how much of that energy came from fossil sources, different fossil sources, nuclear and other fossil, and how many of that came from renewable sources. Now, nuclear is not technically a fossil energy, but it's a mineral-based energy. But it's not renewable, and then renewable energy is, in this case, mostly biogenic energy. So these are the building components we modeled. Structure, subgrade, lateral systems, exterior wall, and roof. So everything we needed for the structural integrity of the building. Now, the non-structural components are not modeled because we made an assumption that the non-structural components of a CLT building and a traditional building would be exactly same. The foundation was not modeled in this particular paper, though there were theories that foundation actually of a CLT building would be smaller in terms of footprint, because CLT buildings are lighter in terms of weight than concrete buildings. So the foundation should be smaller. At that point, we didn't model it. Later on, we did, and I'll share some papers with you on that too. So what we found is that the global warming of both the charring design and the gypsum design of the structural building, after we factored in. Now, going back here, you can see that a CLT hybrid building also uses a lot of steel rebar, concrete, and or the pouring of the concrete that happens on the floor and all that. So the buildings, the hybrid CLT buildings, are not just CLT and glulam. They also have steel rebars and concrete in them, because we were very conservative. But even with the current system, you'll have to use some of that. So when we took everything into account, we saw that there was a 26+% reduction in global warming potential. Some of the impact categories are not significantly different, though eutrophication, which is a water pollution index, CLT buildings fared way better. Smog was almost the same, and acidification was almost the same. Ozone depletion also. So in most of the categories we looked at, CLT buildings performed way better. Few, they're same. But the global warming is the most important, and that's what it fared way better. Now, when we looked at the different components of the building, this is called a contribution analysis. And the 3 bars are the 3 different scenarios for each of the categories. Let's focus on the global warming category here. The global warming category, we see that the structure actually was the biggest contributor for the concrete building, which is the first one, which is 45%, and that fell off quite a bit in the other buildings, CLT buildings. So the concrete aspect of it was the most impactful, but I'll not go into the detail and move on. And so, yeah, these are the benefits. Moving on to the individual components of the building, of the 2 CLT buildings, what we saw that the gypsum wallboard that we avoided in the second scenario was a huge contributor of global warming in the first scenario. So it was a good thing by removing the gypsum wallboard, though the net result was not that magnificent. So However, one of the benefits, okay, we'll talk about, let's talk about the energy demand. So the total energy demand of the wood buildings versus the CLT building were more or less same. Where is different is most of the energy that comes in the wood building comes from renewable energy, and if it's carbon neutral, it does not cause global warming. And most of the energy that comes for the concrete building are non-renewable energy, and that is bad for environment. So though the net energy demand is same, the wood buildings is better because of the biogenic carbon neutrality and sustainable harvesting we do in the United States. The other benefit we need to think about is the carbon storage. And the carbon storage in the CLT buildings are huge, and they would be stored for at least 50 to, or at least 60 to 100 years. So that's a massive benefit of CLT building. And that benefit increases when we are using the charring design, because you're using a lot more wood. In the regular CLT building, with gypsum wallboard, we use 1.5 thousand tons of CO2 sequestered in the wood products or stored. In the charring design, it's 1,000 tons more. So 2.6 thousand tons of CO2 stored. So that's a good thing about using more wood, that you're storing more. But the embodied carbon wise, they were more or less same when we compared. So the conclusion is definitely the CLT buildings are perform better with global warming potential. My later papers, which use the current building code, actually showed that some of the reduction, which we saw is 26.5% in here from structure to structure. Those models show up to a 44 to 50% reduction, and I'll share some of the links with you later on. The charring design helped a little bit in global warming, but the carbon storage potential of the charring design was the biggest. Energy demand wise, more or less, it's a 2% margin. The CLT buildings were using a little bit higher energy. In one of the scenarios, only the charring design scenario. However, when we look at the composition of the energy, the wood-based buildings have significantly lower fossil carbon and significantly more quantity of carbon neutral renewable carbon. This is, if you go to the special issue, you'll find some of the more recent papers where we used this is a special issue, so this has a number of papers, but it also has a couple of papers that came out of our lab and our effort. Let's say it that way. And so those have more recent designs, and they show a higher reduction of global warming when we use the building codes that has been approved. With that, I'll stop. I think I was 2 minutes over from my initial target, but I'm ready for questions if there are any.
Real quickly, can we share your PowerPoint? Can you send it to us and we can share it with our students?
Yes, just before the class started, Pat, I emailed it to you, and
okay.
Please feel free to share it.
Yeah, so you'll get that in Canvas. Now, first question, let me come and ask. Get you to the microphone so he can actually hear you. I'm not translating.
Hi, I just wanted clarification on what the difference was between CLT and glulam products.
That's a very good question. So CLT products are cross lamination. So you take CLT products, and these are panel products. And you put panels first in, let's say, north-south direction, and the second set of panels will come in east-west direction. So it's cross lamination. And you can make big, like plywood, kind of a whole wall out of CLT. Glulam is a beam product. Glulam beams are only, you put glue lamp beams in a same direction. That is, all the beams, all the panels will be glued in, let's say, north-south direction, and we are paneling it. So glue lamp beams is a beam product, and it can be used as a column or a beam. And CLT is a panel product, and you can make the whole wall out of CLT because it can be square or rectangular shaped. Glue lamp beams are long; they're rectangular but long. Does it explain?
And if you want to see examples, the Andy Quattlebaum Center out at the Snow area, that building has hybrid steel columns, but the beams and the ceiling and the floor on the second floor are CLT panels. So it's very evident if you go out to Andy Quattlebaum anywhere and look up on the porch or in the building, you will see glue lamp beams and CLT panels. Are there other questions? Yes.
What does the process for replacing like columns that have been charred look like? Because I assume like once they get burned, you would probably have to replace them.
So essentially, you're creating a fire protection. So if that house is in a fire, most likely you'll not go back and live in there, just like a regular fire. But the whole idea of charring design and fire protection is that the building doesn't collapse. It doesn't, in the worst case scenario. However, if a certain section of the beam gets charred and you can go back and live in that building, most likely you will put some gypsum board on top of it. You'll have to assess the structural integrity of the building and all that. On that note, I just want to highlight that it's easier to switch wooden beams, glue lamp beams or LVL, as compared to non-wooden beams like steel and concrete combined beams. But that would be a question for a structural engineer more than me. But I think there are a lot of structural engineers, at least I work with at Clemson, who would be able to give you a better answer for that.
Yeah, and I will just add, we're working on it, but there is the possibility of encasing. If you still have enough strength in what's left of the beam, you can encase it in either wood or gypboard. And then there are possibilities of if the building is designed and connected appropriately, you may be able to actually replace pieces. So all of that is in the process of development with the wood. And I will say that in the case of steel and concrete, it will depend on temperatures and the strength that's left in the steel. And that would also include rebar. And in concrete, we would also have the potential for spalting. And that may have reduced the strength of the concrete. And so you may not be able to eat it. And so it's just a matter of can you or can't you, and the severity of the fires and stuff. Other questions? So I will say one thing, paper, I'm coming to you, paper does get recycled, and life cycle assessment does handle and allow for you to recycle. And paper products, not facial tissues and toilet paper, but a lot of non-sanitary products do get recycled, and about 60% of paper is recycled, and you can usually recycle them 3 to 6 times before they end up being too small to recycle again and they go to a landfill. Life cycle doesn't handle landfills very well, but a lot of research in landfills that is cited by the EPA does indicate that you can actually put paper in a landfill, in a modern landfill, and it will stay there for centuries and not a year. So if you throw it out on the street, it's going to degrade. But if you put it in a modern landfill, it may be there for decades to centuries. So it is a very long-term carbon storage issue. And hopefully Indra is going to be adding that to LCA of paper products soon. Do we have any questions?
Actually, Pat, that is the end of life modeling actually can factor in the landfill modeling and the emissions from the landfill. And just a quick statistic of what you just said, there is an EPA worm model which says almost 88% of all the biogenic carbon, including paper and lumber products in dry landfills, live in the landfill for over 100 years without any degradation, 88%, and that is amazing.
That's a lot. Concrete, it still lives in a landfill for a long time too. It's just, it's not going to get ever down. Were there any questions online? Do we have any questions that someone who is online would like to pop in and ask? And then I have another question while you guys are getting ready. I have a question from the audience. Yes.
I wanted to ask about the cost difference of a wooden building and a steel reinforced building the way we do, normally. And I also wanted to ask, you also said during the presentation, you said a lot, you guys were conservative. What did you mean by that?
Okay.
Did you mean you were conservative with the estimates?
Yes. So when I said conservative modeling of how much, because at that point we are replacing some wood, some concrete, and using glulam and CLT. So we were actually reinforcing a lot of the displaced with additional material and all that. So because how much of CLT we could use, we were reducing the amount of CLT and glulam, the wood we could use, and we were not displacing a lot of concrete and steel. We're still keeping a lot more in the system. So we were over-engineering the building in a way than we need to. And that's a conservative part of it, so that the building doesn't fall down. The other part of your question was, sorry, I just forgot. Can you, Pat, can you remind me quickly?
The cost difference between.
The cost, yeah. So the link towards the end I gave you, there is a paper on the cost. Now, cost, there are two aspects of the cost. One is when you build a building, there's a cost of materials, and the CLT and buildings generally have a little bit higher cost of materials. The second cost comes in the cost of actually building the building, that inside cost. And CLT building in Europe, when the builders and the architects and the system is more efficient, we are still kind of getting there. But in Europe, they saw there's at least a 25% reduction in the cost, on-site cost, because you don't have to pour concrete and all that, or you just bring in the material almost like Legos from a factory and put it in. So a CLT building takes significantly less time to build. It's in some cases we saw 50% time, like 6 months to 3 months, in some cases even less. And so that's a cost saving. So the net is depending on how efficiently you're building and how your wood products industry is. In the US, we do have a potential for it to be a cost or they are cost equal almost. At this point, it costs a little bit more because we do not have a lot of CLT factories, and our woodworking industry is still kind of learning the ropes. But in Europe, they have found that it actually, wherever labor is very expensive, actually the cost of building with CLT may end up being beneficial, like it would cost less.
Just to add, the Andy Quattlebaum building was designed and estimated and had to come out as a cost less option, or we would not have been able to use the wood. One of the key savings has been we are using the exposed wood as the ceiling of the first floor, and the ceiling of the second floor, and the ceiling in the outside barn area. And those do not have gypsum board on it. And so there was almost $100,000 less of gypsum board cost because we didn't cover up the ceiling. And so the total building cost for that building as designed came in lower than an equivalent building that would have been built with steel and concrete and had to have gypsum board coverings on the steel and the concrete for fire protection. So there is a lot of what goes into the total building cost. And wood does vary of cost seasonally. And during COVID, wood cost a lot of money. And right now wood's gone down in pricing very significantly. So the price has gone down over time.
And
So
just
it is total cost.
And Pat, just to add to what gypsum board is very important because it is a cost issue, and gypsum board is also a carbon issue. It's a extremely carbon intensive product, fossil carbon intensive product, and expensive. However, if you're building very tall buildings, the code requires some gypsum use. So at times it becomes almost you cannot avoid using gypsum if it's a 8+ storied building. And but if you can, like 8-storied building, you can avoid gypsum, which we did, and it would be a beneficial thing. So yes, I agree with that point.
Okay, so it's 1:34, so we're running a little long. If you want to stay and ask a question, please do so. If you need to leave, do not forget to sign in because we are required to take roll. So please sign in at the back of the class. And Indro, I would like to say thank you very much. And everybody, before you go, let's give him a big round of applause. And we'll put the PowerPoints out in Canvas so you can have access to these materials for your future use. Thank you, Indro. This was great. We really appreciate it.
Thank you, Pat. And thanks to the class for being patient and listening.